Welcome back. Today I will be talking to you about double integrals over general regions, and that is opposed to double integrals over rectangles, which we talked about last time. So first let's just take a little look at the picture we have here. In the picture you see we have an XYZ coordinate system, and in the XY plane we have a region D. Okay, and I've got dotted lines going around region D. Here's our region D in the XY plane. And then above region D, you have some surface. Okay, so up here, you have some surface above region D. And what you might be asking is, what is the volume under that surface? So if you wanted to find all this volume underneath this surface, how would you do that? Okay, so we figured out how to do that already. If that region D is a rectangle in the XY plane, so what do you do in general if that region D is not a rectangle? So that's what we want to talk about today. Okay, so what I want to do is let's start with a definition. So definition: a plane region D is said to be of type 1 if it lies between the graphs of two continuous functions of x. Okay, so what do I mean by this? Another way of writing that is that D is equal to the set of all points xy such that A is less than or equal to x is less than or equal to b, and y lives between g1 of x is less than or equal to y is less than or equal to g sub 2 of x. Okay, so that's what we mean by D, but let's actually draw that in 2 dimensions. So what are we talking about here? So let's say we have an xy axis. Here's my x, here's my y. Then what we mean is that D lies between A and B in the x direction, and it lies in between 2 functions, a lower function and an upper function in the y direction. So one way that I might draw that is like this. So let's say there's an upper function, call this one g sub 2 of x, and some lower function, call this one g sub 1 of x. And now the region D is what's in between those two. So that shaded region is what we would call D. So one way to think of this, so a type 1 region is in between some x value A and some x value B, but if it were rectangular, then there would be a y value C and a y value D. But this is not a rectangular. This lies between 2 functions of x. So a top function in the y direction and a bottom function in the y direction. Okay? Let me draw another type 1 region just so we can get another thought of what these things might look like. So here's my x-axis. Here's my y-axis. Here's A. Here's B. So here's another way that this might look. So let's say that I have this as my region D that I want to integrate over. So there's my region D. So up here on top is my g sub 2 of x function from here to here. And this is my g sub 1 of x function that starts here and ends here. All right. So both of these would be considered type 1 because in the y direction, the top of the region is a function of x, and the bottom of the region is a function of x. Okay, so if we have a type 1 region, how do we integrate it? Let me write that down real quick. So if f is continuous on a type 1 region, D, such that D is what we're expecting. D is equal to the set of all x, y's such that A is less than or equal to x is less than or equal to B, and g1 of x is less than or equal to y is less than or equal to g sub 2 of x. Okay, so in other words, D is exactly the kind of region we're expecting. Then we get the following, that the double integral over D of f of xy dA is equal to the integral from a to b, integral from g of sub 1 of x to g sub 2 of x of f of xy dy dx. Okay, and this is important, the order of the dy and the dx, because the y's are ranging from a function of x to a function of x, so the y's are in between a function of x and a function of x, and the x's are in between a and b. The x's are in between a and b. All right, so for a type 1 region, we always want to integrate the y's first if we can, and then integrate the x variable. Okay, so y gets integrated first, x gets integrated second, if possible. Okay, so knowing this, let's try one of these and look at an example of how this would work. So here's an example. Let's evaluate the double integral over some region D of x squared plus y dA, where D is the region bounded by y is equal to 2x and y is equal to x squared. Okay, so a couple things. First of all, this is the function that we're actually integrating. For right now, I'm just going to leave that alone because I need to figure out what are my limits of integration here. The only thing that I really care about this x squared plus y is recognizing that, in fact, that is a continuous function. So I can switch the integral into an integral from a to b, integral from g1 of x to g2 of x of this function, dy dx. So I need to figure out what's the region here. Let's look at the region. So let's graph it. So first of all, I get y is equal to 2x. So y equals 2x looks like this. This is y equals 2x. And then y equals x squared does something like, let's see, it goes through here. At 2, we get 4. So we get this little region in here, and that is going to be the region that we're trying to integrate over. Okay, so we can see that this intersection point right here, that's 2, and this is 4. All right, so now I want to set this up, and I want to recognize, is this a type 1 region? And it is, because this region that I'm looking at on top is a function, and the bottom of the region is another function. So which of the two functions is on the top? Well, the line is. And the line is y equals 2x. This parabola is y equals x squared. So the top function's the line. The bottom function is the parabola over that region. So if I'm setting this thing up, I need to integrate from an x value to an x value. Well, the starting x value is 0, and the ending x value is 2. Then I need to integrate from a function of x to a function of x because this is a type 1 region. So what's the bottom function in this case? That's y equals x squared. So down here, I get an x squared. And on top, I get the line, which is 2x. So I'm integrating from x squared to 2x. Then the function goes in here, which is x squared plus y. That just comes from the original integral. And then I get dy dx. So if I integrate this guy, I will get my answer. So let's go ahead and integrate that and see what we come up with. So I'm going to transfer that to a new page, and we will do it. So we want to integrate from 0 to 2, integral from x squared to 2x of x squared plus y dy dx. And remember, when I do this kind of thing, I do this whole integral first and just leave the integral from 0 to 2 and the dx alone until I'm done with that inner integral. So let's do it. So I get integral from 0 to 2 of. All right, so we're integrating here with respect to the variable y. So the antiderivative of x squared with respect to the variable y is x squared y. And the antiderivative of y with respect to y is plus 1/2 y squared. And that's going to be evaluated from x squared to 2x. All of that dx. Now, remember, what is it that we're plugging in the 2x and the x squared for? We're integrating the y. You don't want to plug those things in for the x. You've got to plug them in for the y, and be very careful. Remember, we're integrating right now with respect to y, so we're plugging in this 2x and this x squared for our y's. So in other words, when we're done with this step, all that's left should be x's. No y's should be left. And that's the goal. So get rid of the y's. That's the goal of the first step. So let's do it. Let's plug in the 2x and the x squared. And what I get is I still have this integral from 0 to 2. Then if I plug in 2x for y, I get x squared times 2x plus 1/2 of 2x quantity squared, okay, minus, now we plug in the x squared, and I get x squared times x squared plus 1/2 of x squared quantity squared. All of that dx. So let's simplify a little bit, and I get integral from 0 to 2 of, okay, so I get 2x cubed plus, so if I square the 2x, I get 4x squared divided by 2 is 2x squared. Then I get minus x to the 4th. Then I get minus 1/2 of an x to the 4th. All of that dx. Let's see here. Yeah, so let's keep going. This gives me integral from 0 to 2. If I combine a negative x to the 4th and a negative 1/2 x to the 4th, I get minus 3/2 x to the 4th plus 2x cubed plus 2x squared quantity dx. And now I'm in the perfect position to take an antiderivative. So let's go ahead and take our antiderivative. Antiderivative with respect to x of negative 3/2 x to the 4th would be negative 3 over 10 x to the 5th. Antiderivative of 2x cubed would be plus 1/2 x to the 4th. And antiderivative of 2x squared would be plus 2/3 x cubed. And then I want to evaluate that from 0 to 2. So let's plug in the 2. Okay, what's 2 to the 5th? I suppose 2, 4, 8, 16, 32. So I get minus 3/10 times 32 plus 1/2 times 16 plus 2/3 times 8. And then when I plug in the 0, I just get all zeros. So this is it. And now we just need to simplify this a little bit. Okay, what do we got here? This, I could simplify this a little bit and get a 16. So 3 times 16 is 48. So I get minus 48 over 5. And then 16 divided by 2, of course, is just an 8. And then 2 times 8 divided by 3 is 16/3. And we could do a little bit of getting a common denominator, combining things, and we will end up with 56 over 15. Okay, and what is this 56 over 15? This would be the double integral over that region D of this function f of xy. Okay, so that is an example of a double integral over a type 1 region. All right, so now let's talk about the other type of region that we could encounter, and that is that if we have a region that is a type 2 region, then the region looks slightly different. Let's draw a picture down here at the bottom of a type 2 region. And this is a region where instead of x ranging from a constant to a constant, y ranges from a constant to a constant. So y goes from C to D. and then x ranges from a function of y to a function of y. So let me draw one of these so that you can see what I'm talking about. So, for example, you might have something like this. So here is a region D, and maybe it goes from some y value, C, to some y value, D, and then x's range from some function. Okay, so here's a function right here to another function. So this is h1 of y to h2 of y. And then here's my region D. Okay, so very similar to a type 1 region. It's just that instead of going from a lower function to an upper function in the x direction, now we're going from a lower function to an upper function, where the lower and upper functions are functions of y, not functions of x. Okay, let me draw one other type 2 function just so you can kind of see. So maybe we have something like this. Here's one function. Here's another function. So this is my lower function, h1 of y. And up here is my upper function, h2 of y. And here's my region, D, where this is C, and this is D. There's my capital D region. Okay, so you can kind of see what a type 2 region is. So let's do a quick example of a type 2 region. So, example, let's evaluate the double integral over capital D of xy dA, where capital D is the region bounded by the line y equals x minus 1 and the parabola y squared is equal to 2x plus 6. Okay, so the first thing I want to do here is I want to draw the region D in the xy plane. So let's draw my xy axis. Here's my x, here's my y. And I have the line y equals x minus 1. Okay, so down here at minus 1, I have a function with slope 1. So go this way, this way. Okay, so this is y equals x minus 1. And then I get y squared equals 2x minus 6. Okay, so y squared equals 2x minus 6. Where does that hit the y-axis? In other words, if x is 0, what's y? So if x is 0, we would have that y squared equals 6. Is that correct? So that means that y would equal the square root of 6 and the negative square root of 6. So square root of 6 and negative square root of 6 down here. So, and then this is a parabola and it opens to the right. So if we come back also, what if y is 0? If y is 0, x is minus 3. So we get this parabola. It kind of goes like this. This is, of course, a little bit rounded here. Okay, so this is at minus 3. And so we get this region that's trapped between the two. Okay, so first thing that I notice here is that this is a type 2 region. In other words, it's bounded below by a function, and it's bounded above by a function. And these need to be functions of y, not functions of x. So that means we need to solve these things and make them x equals a function of y. So what is the line? The line here, y equals x minus 1, could be rewritten as a function of x, and we would write that x is equal to y plus 1. Okay, what about this parabola, which is y squared equals 2x plus 6? If we rewrite this guy as a function of x, we get that 2x is equal to y squared minus 6, or we could write that x is equal to 1/2 y squared minus 3. Okay? So the top function in this case, and remember, if in doubt about which one's the top function and which one's the bottom function, make a number line. Which thing is bigger on a number line? Things to the right side or things to the left side? Well, the bigger things are on the right. So this is the top function. This is the bottom function. So use a number line if in doubt of which is the top function, which is the bottom function. But we see in this case the line is the top function. So here's my top function. The parabola is the bottom function. Here is my bottom function. And now I'm ready to set up this integral, other than the fact that I don't know where are these two intersection points. What am I integrating to in the y direction between what, c and d? Well, to figure that out, I could just set these two equal to each other and solve for y. So let's go ahead and do that, and then we'll be ready to set up this integral. So I'm going to set these two equal to each other. So in other words, I have that y plus 1 needs to be equal to 1/2 of a y squared minus 3. And now let's solve for y. Let's move everything over to the right side. If I do, I get 0 equals 1/2 of a y squared minus y, then minus 1 minus 3, or 0 is equal to 1/2 y squared minus y minus 4. I could multiply everything by 2, and then I get y squared minus 2y minus 8. Okay? That factors, so let's factor it. This is y, let's see, what would it be? Minus 4 times y plus 2. So y is equal to negative 2 and positive 4. So in other words, I'm integrating this thing. My picture looks like this, correct? I have this parabola and I have this line. So now I know that this point is at minus 2 and this point is 4. So now I'm ready to set up this integral. Okay, so the integral here is going to be the integral from minus 2 to 4, integral from the bottom function in terms of y, and we said that the bottom function in this case is the parabola. Well, the parabola is x equals 1/2 y squared minus 3. And the top function was the line. The line is x equals y plus 1. Now I put in my function, and my function in this case is just x times y. And then this is dx dy. And now we're ready to integrate this thing. So first, we're going to integrate this part. So we're going to take the antiderivative of xy with respect to the variable x. When I do, I get integral from -2 to 4 of antiderivative of xy with respect to x is 1/2 x squared y. That's evaluated from 1/2 y squared minus 3 to y plus 1 dy. So let's plug things in, and I get integral from -2 to 4. And remember, we're plugging in for x this time because I was integrating with respect to x. So I plug in y plus 1 for x. So I get 1/2 of y plus 1 quantity squared times y minus, now I get 1/2 of 1/2 y squared minus 3 quantity squared times y. All of that dy. Okay, so now we need to square this out. So I'm going to go through this rather quickly, but make sure to go through and check all my work. Make sure that you agree with everything I do. So I get a y squared times y, which is y cubed, times a 1/2. But notice here that there's a 1/2 out in front of this term, and there's a 1/2 out in front of this term. So I'm just going to factor out a 1/2 to make life easier on myself. Okay, so we can kind of forget about these 1/2s now. I factored the 1/2 out in front. Okay, so now I just need to look at this piece, and I get y squared times y, which is y cubed. Then I get 2 times y times 1, which is 2y times y is 2y squared. And then I get 1 squared, which is 1 times y, which is plus y. Okay. Then the 1/2 is gone, so I square the 1/2 here, and I get, so I'm just looking at this, but remember there's a negative here. So I square the 1/2, and I get 1/4 y to the 4th times y is y to the 5th. So I get minus 1/4 y to the 5th. Then I get 2 times the first times the second, which is y squared times -3 times a negative is positive 3. So I get positive 3y cubed. And then finally, I square the -3, which is 9. So I get minus 9 times y dy. Okay, so let's combine some like terms. I'm going to erase really quick so I can do this. I'm going to leave what I have on the bottom here, and then we'll work at the top so that we can see what we're doing. Okay, so what we have here is this is equal to, I still have a 1/2 out front, and now I'm going to take, I could take an antiderivative right now. Maybe I could clean it up a little bit first. So it's 1/2 integral from -2 to 4. And now let's see, I have a minus 1/4 y to the 5th. So that's gone. Then I have some y cubed terms. There's a 3y cubed and a y cubed, which gives me a 4y cubed. So that's done. I have 2y squareds. So that's done. And then I have minus 9y plus a y. So minus 8y. All of that dy. Okay. So now I'm ready to take this antiderivative. Oops. Okay, so let's do it. So I still have a 1/2 sitting here. Antiderivative of this first guy is minus 1 over 24 y to the 6th. Then I get plus y to the 4th plus 2/3 y cubed minus 4 y squared, evaluated from -2 to 4. All right. So let's go ahead and plug things in. And I still have this 1/2 sitting out front. And now we want to plug in the 4. Okay, so we get minus 1 over 24 times 4 to the 6th plus 4 to the 4th plus 2/3 times 4 cubed minus, well, 4 times 4 times 4, which is 4 cubed. Okay, all of that minus, plug in -2, and I get minus 1 over 24 times -2 to the 6th plus -2 to the 4th plus 2/3 times -2 cubed minus 4 times -2 squared, with -2 squared, and that's it. Okay, so there's a little bit of math to do here. We need to just kind of add up all these numbers. We do so, and we would get 36. So go through, check this, make sure that you do agree with me that that is 36. And that is my example for you of a type 2 region. Now, you may be thinking, these take a little bit more work than a double integral over a rectangular region. And that's absolutely true. Typically, these take more thought in setting them up, and they take more thought in actually computing the integral. So these are a little bit trickier than just the rectangular regions. But I find that if you take your time and you really check your work, these are very doable. Okay, let's try another example. I'd like to evaluate the iterated integral from 0 to 1, integral from x to 1 of sine of y squared dy dx. Okay, so everything's nice and set up for me. The first thing that I would need to do is take an antiderivative of sine of y squared with respect to y. This is a bummer, because actually, if you think about it for a minute, I have no idea what that is. I don't know the antiderivative of sine of y squared with respect to y. I don't know that antiderivative. And so that makes this kind of impossible the way that it's set up. But what I can do is I can do something kind of tricky, and that is, let's go to the region. Let's look at the region that I'm integrating this thing over. So now we have to look at these two integrals right here and kind of use those integrals to see what is the region. Well, this is saying that in the x direction, I'm integrating from 0, here's 0, to 1. And in the y direction, I'm integrating from y equals x, which is this, y equals x, to y equals 1. Here's 1, and so here's the line y equals 1. So I'm going from 0 to 1. The bottom function is y equals x. The top function is y equals 1. So here's my region. Okay, so this is the region I'm integrating over, and it's not working out so well because I don't know the antiderivative of sine of y squared. But I could certainly take the antiderivative of that with respect to x. I don't know the antiderivative of that with respect to y, but I do with respect to x. So what I'm going to do is I'm going to say, well, this was written as a type 1 region. So can I switch it and think of it as a type 2 region? Well, if this were a type 2 region, then this is now over here. This would be the top function. This would be the bottom function. But I'd have to write those in terms of x equals a function of y. Well, this one's easy. It's x equals y. And then what is this as a function of y? This is the function x equals 0. So I have a new top function. I have a new bottom function. And so let's rewrite this thing. This would be the integral. And now what am I integrating to in respect to y? I'm starting at y equals 0. I'm ending at y equals 1. So I'm integrating from 0 to 1. Now the top function is this line, which is x equals y. And that is incorrect. The bottom function here is x equals 0. The top function is x equals y. And now my function is still sine of y squared, but now I'm integrating with respect to x first, and then with respect to y. Okay, why is that good? Well, because now I know the antiderivative of sine of y squared with respect to x, because that's just a constant with respect to x. So now let's look at this iterated integral and see what I can do with it. Okay, so let me rewrite this. So I've got the integral from 0 to 1, integral from 0 to y of sine of y squared dx dy. Okay, so I'm doing this piece first. So this is just equal to the integral from 0 to 1 of sine of y squared times x evaluated from 0 to y dy. Now I need to plug in the y and the 0 for x. If I do, I get integral from 0 to 1. If I plug in y for x, I get sine of y squared times y. And then if I plug in the 0, I get 0. So it's just this dy. Okay, well this is just a nice u substitution problem where u is equal to y squared and du is equal to 2y dy. So I need a 2 inside. So I need a 1/2 outside. So I can rewrite this as 1/2 integral so the 2y dy all become du, and here I'll have sine of u du, and now I need to switch the limits of integration. So if y is 0, u is 0, and if y is 1, u is 1. So I get integral from 0 to 1 of sine of u du. Okay, so let's take an antiderivative. I get 1/2. Antiderivative of sine of u is negative cosine of u evaluated from 0 to 1, which is equal to 1/2 of negative cosine of 1 minus negative cosine of 0. Okay, so what is, of course we have a negative and a negative, which is a positive. And what is cosine of 0? Well, cosine of 0 right here, that is 1. What is cosine of 1? Well, we don't really know that, so I'm just going to leave it as cosine of 1. So first of all, I get 1/2 times negative cosine of 1, so I get negative 1/2 times the cosine of 1, and then I get plus 1/2 of the cosine of 0, which we know is 1. So this is my answer. I can't really do any better than that without writing out some sort of a decimal, because we don't really have a nice expression for cosine of 1. But we did get the answer, and notice that in its original form we had no shot at getting the answer. But once we changed the order of integration, so instead of starting with dy and then dx, if we switched the order and did dx first and then dy, we were able to integrate, but in its original form we were unable to integrate. So this is a nice little trick you can use if you cannot integrate in one form like dy dx. Try switching it first to dx dy, but you have to go back to the original region. You have to look at the original region, because it's not going to just be as simple as switching the two integral signs. That's never going to work. You have to look at the original region and completely rewrite your integral. Start from scratch. Okay, very good. All right, let me share with you a few more things, and then you will be ready to try some of these on your own. Okay. The first thing is that all of these nice properties that we have for integrals often work for double integrals as well. So if I have a double integral over region D of f of xy plus g of xy dA, then that's the same thing as the double integral over D of f of xy dA plus the double integral over D of g of xy dA. So this, we typically call this the sum rule for integrals, and it works for double integrals as well. I can break them up over a sum and just take the double integral of each of those functions separately. Similar with the constant multiple rule. So if I have some constant times f of xy, I could move that constant through both integral signs and write this as c double integral over d of f of xy dA. So we have this nice constant multiple rule. Another property that it's good to know is that you can break these double integrals up over regions. So let's say that I had some region in the plane. Here's my xy plane, and my region D. And let's say that I wanted to break D up over two regions and say that this is D1 and this is D2. So in other words, D is equal to D1 together with, or union D2. So it's kind of like this is my set notation for just join those two guys together or union them to get my big set D. Then the double integral over D of f of xy dA is equal to the double integral over d1 of f of xy dA plus the double integral over d2 of f of xy dA. Okay, so that if you want to, you can integrate over two separate regions that might be easier for you to integrate over, and then just combine those two together, as long as those two regions together give you D. Okay, so those are some tricks that we can use. These are tricks that we've kind of seen before in 2 dimensions, but it does expand and generalize to 3 dimensions as well. Okay, time for some homework.